Hi everyone, my name is Cameron and today we're going to be looking at space. Specifically, we're going to be looking at the formation of the solar system, the life and history of a star, planets, satellites, orbits, the expanding universe. So how do we know it's expanding? And the beginning and future of our universe. So let's start with how the solar system formed. To do that, we've got to begin with the center of our solar system, which is the star, or the sun that we like to call it, okay? So how a sun forms, okay? Gases are going to be pulled together by their own gravitational attraction. It's important to know that everything, as soon as it has a mass, is going to have a gravitational pull, okay? You have a gravitational pull. This bottle over here has a gravitational pull, okay? It's just very minute. But in space, these gases are going to start attracting to one another. Okay, these particles in the clouds are then going to be pulled together by their own gravitational attraction, as we say, and it's going to become denser and denser and denser, okay, or more and more dense, you could say. And eventually it's going to become what is known as a protostar. So a protostar is basically like a gas giant. Okay, so you could consider Jupiter as a protostar. Okay. Eventually, this protostar is going to get so dense and so hot that fusion is going to occur. Now, fusion is when hydrogen atoms are going to fuse together to become helium. This is going to release a lot of energy, and it's then going to form a star. Okay. We call this the main sequence stars, though, because this idea of fusion and generating enough energy to actually become a fireball instead of Jupiter, okay, would separate the two from each other. That and the size of the sun is massive, okay. But Jupiter had the ability, they think, to become a star, but it's a failed protostar, is what they call it. So we're looking at the life cycle of the star. So it goes from protostar, okay, to main sequence. Now, depending on the size of the star initially, it's going to go through different sequences. Okay, stars that are like our sun in size are going to go from a main sequence star to a red giant, then a white dwarf, then a black dwarf. Okay, but if their mass is greater, and there are stars that are way bigger than our sun, I suggest you go look online for the size comparisons of stars. It's incredible. Okay, but it can go from a main sequence star then to a red supergiant, a supernova, a neutron star, and or then will become a black hole if its mass is big enough. Okay, so now let's take it down to scale. Okay, so now we're going to be looking at planets, satellites, and orbits. Okay, so the force of gravity between a planet and a sun keeps the planet moving along an orbit. Okay, the force of gravity between a satellite and a planet keeps the satellite moving around its orbit. Okay, I say now a satellite and a planet because when we say satellites, we're not just talking about the machines that we put in space. The moon would be considered a satellite. Okay, so other planets also have moons and therefore have satellites. Okay. So the force of gravity on the orbiting body in a circular orbit is towards the center of the circle, of course, right? So think of it as those people in the Olympics that throw around a metal ball on a wire, okay, and they spin around in a circle. The center of gravity is going to be that person, okay, as the planet or the satellite gets spun around them. So as a body in a circular orbit moves around the orbit, the magnitude of its velocity does not change. Okay, so its speed doesn't change. Why is this? Because there is no friction in space. Okay, or very, very little friction in space. So as soon as that thing has speed, as soon as the satellite has speed going around the Earth, its speed will not decrease unless something hits it, right? The direction of its velocity continually changes, and it's always at a right angle to the direction of the force. So it experiences an acceleration towards the center of the circle. Okay, so the direction of it is going to change. Okay, as it gets closer and closer to the center of the circle, which is what it's trying to do. This direction is going to change. But to stay in orbit, okay, to prevent itself and to stay at a certain distance away from orbit, it's going to have to be moving at a certain speed around the larger body. Okay, so too slow, it's going to crash into the Earth. Too fast, and it's going to shoot itself into space. But there's going to be a perfect speed where its centrifugal force pulling it outwards and the gravitational force pulling it inwards is going to equal. And then it won't change its position. So, the expanding universe. So, how we are going to know if a star is moving away from us or towards us? How do we know if the universe is getting bigger or smaller? It's going to be based off studying the light waves that it is producing. Okay, so if the light waves of a star are sort of red light waves, okay, we call it a red shift. It's going to be moving away from us. Okay, if the light waves are more blue, it means it's coming towards us because the wavelength, the length between the light waves coming from that star are going to be decreased, and therefore it's going to come off more blue. If it's going away, they're going to increase, they're going to come off more red. Okay, so the faster a star or galaxy is moving relative to you, the bigger the shift is. Okay, and the distant galaxies are moving away from the Earth, the whole universe is going to be expanding. Okay, so when it comes to the beginning and future of the universe, okay, it's theorized that it started with a Big Bang. Okay, a part in space that was incredibly dense, exploding, and giving birth basically to all the matter and all the energy in the current universe. Okay, we expect that it is constantly expanding. It is like an explosion coming out, and we are at the peripheries, the edges of this explosion. Okay, and we think that after the Big Bang, this high energy electromagnetic radiation should have been produced very soon afterwards, and the existence of cosmic microwave background radiation can be explained only by the Big Bang theory. When you put on your TV and it has that static fuzz, that is cosmic background radiation interfering with the antenna of your TV. Okay. The distant galaxies are accelerating away from each other. So scientists think that they are doing this through something called dark energy that's causing the acceleration. And the stars and the planets are actually only a small amount of the matter that our universe is made up of, because the rest of it they believe is something called dark matter. Okay, which is kind of like antimatter, which is kind of like not matter. Okay, all very theoretical, all very interesting. So, my name's Cameron, and I'll see you in the next subject, as this is our last chapter. I hope you've understood this physics. If you still need some help, please give Feynman an email, book a session, and we can go through some examples, and get you ready for that test. Okay, I'll see you next time.